So in this video, I'm going to be doing the Cryptopals challenges. I'm going to do set 1, and I'm going to do it in Python 3. And full disclosure, I'm not a Python 3 expert by any means, but I know a lot of people use these challenges as a way to teach themselves how to program or how to learn cryptography. But I feel like I know Python and cryptography well enough that if you are watching this, hopefully you do get something out of it. But honestly, I'm just making this video. It was a New Year's resolution. I want to start trying to make some content, but since I've never done it before, I know it's really going to suck, and I struggle pretty hard with perfectionism. And since I know it's not going to be any good, I end up like stressing about it, and I put way too much time into it, and then I just end up getting like frustrated, and I never actually end up doing anything. So I'm decent enough at Python and I understand cryptography well enough. I figured I could probably just like sit down and go through all these. It's kind of like would be in my comfort zone, and so then I can just like crap all these out and do it in one take and just put the video up, and hopefully that gets me over the hump. I don't know, maybe I'll be able to keep at it, and in a couple of years, after I've made a bunch of videos, I can watch this one again and be like, ugh, and be pretty embarrassed about it. But I mean, the truth probably is like no one's watching this anyway, so who cares? Just get over it and I don't know, make something. So with that out of the way, let's jump into it. So I've like looked through all these, so I know what's coming up, but I haven't really like tried to do any of it because I thought it might be helpful just to like have somebody who can do it like sit down and do it. So that's kind of what I'm going for here. So in this first challenge, let's go ahead and so also I'm doing everything in Sublime Text. I'm not using an IDE or anything, since really I don't code Python for my job or anything like that. And as I'm trying to learn Python, I find anytime I want to learn language, I do a lot better if I just do like in a text editor, because the IDE kind of like, I don't know, helps me get lazy and I forget like what methods I'm using, because I just use autocomplete for everything, and then I find if I don't have the IDE, I like can't write any code at all. So I just tend to like not use an IDE unless like I feel like I know it really well and I'm trying to like be productive or something. So anyway, so the first challenge, basically we have this hex string and we want to convert it to base 64. So when we're done, it should look like this. So let's go ahead and, oops. Oh yeah, so also like, I'm not going to get like super in depth. So like if you don't know what, if name equals main and all that stuff is, or like what functions are, like this definitely isn't the video for you. But there's like a ton of really good videos and resources and, all kinds of stuff out there to like teach you how to program. So I'm going to try and do it as like thinking you're a beginner in Python and a beginner in cryptography, but like not necessarily like a super beginner in Python. So I don't know, hopefully I can find like a decent balance, and like if someone actually does watch this, they get something out of it. But so anyway, then main function. And so what we're doing is we're taking this string, which is in hexadecimal. So just call it hex1. And we want it to end up like this. So we'll call that our answer. And our result will be 4. And then I'm not going to do like write any tests or anything, but I will make a little print statement to see if we got it right. Oops. And this is just an F string, which is like a Python 3 way to like format strings easily. Anything you put in the curly brackets, it actually evaluates and displays. So if we evaluate answer equals result, it'll either return true or false. And then we'll go ahead and print out the result just in case we get it wrong, and then we can see what we ended up with. So it's just an easier way to debug. Now obviously if I run this now it won't work because we haven't written our hex to base 64 yet. And we're going to take a string and we're going to output. So in like, one of the hard things with trying to figure out is like what format to put your inputs and outputs in. And with cryptography, you do a lot of stuff in bytes. So I always just try and keep everything in bytes. So like bytes in, bytes out. I find that's like the easiest way for me to remember like what my functions are doing. In this case, I'm going to go ahead and leave the input as a string because we're actually taking a hex string, but I'm still going to go ahead and output bytes. So let's go ahead and add, just for giggles, we'll add some error checking, and let's import our base 64. And we're encoding. Oops, from base 64. And here we're going to check to make sure that everything in the string we're importing is actually in hexadecimal. So we'll do 4C in data, and then we'll check 4C in string dot, I think it's hex digits. And this is just going to enumerate over everything, and it'll return, I guess it'd be a tuple of whether or not each character in that string is one of the hex digits. But we want to make sure and check if they're all hex digits. And so if they're not all hex digits, then we will raise an error. Hexadecimal. So now we have our fancy error checking. And so whenever you take anything and put it into base 64, base 64 takes bytes. That's what base 64 does, is encode bytes into the 64 possible characters. So we need to convert our string, which is currently a hex string, into bytes. So that'll turn that into bytes, and then we can go ahead and encode it. And return it. So if I did that right, this should run, and let's save it. Aha! I spelled it challenge 01. I'll fix that in a second. So return. Oh, I forgot the B. So yeah, one of the downsides of no IDE result is not. Is all your little typos and everything, when you go to do it, you end up seeing all the stuff you missed. Well, okay, so first off, let's, I'll do it afterwards because it'll change the file in the Sublime. Anyway, so we see we got it wrong, but what's happening is we're getting this is a byte string back, so the B here means it's a byte string. If you actually look at what we're trying to get, we see that it's all the same strings, it's just this is a byte string. So when it evaluates answer equals result, it's going to get false because we're comparing bytes to strings. And then a byte string, it probably you're going to spend, at least this is how it worked for me. I spent a lot of time confused about when is something displayed like this, and then how do I know when it's like, you'll see it a lot of times as like, let's do, what's the letter A? 61, I think. Like, when do you see an X, and then how do you escape, and then Python 2 was different than Python 3, but I didn't really know Python 2 because I wasn't doing any of this when that was sort of the main one, but like you'll still find stuff written in Python 2, and then, I don't know, it was super confusing for me. But basically, kind of, you want to think that this is just, you can think of this as an actual, like, I don't know what the underlying structure actually is, how it stores it, but in my head, I just think of this as an array of byte values. And it's just displaying it to me as the ASCII character representations of those byte values. So like in my head, I'm thinking this is actually the byte value in hexadecimal would be 61, in decimal would be 97. So like character value 97 is A, but whenever you have these X stuff, that it's in hexadecimal because bytes, because it makes it easier if you're converting it to binary, like displaying bytes in hexadecimal is like just an easier way to work with it. And then like if you actually wanted, like say I somehow wanted to actually have the or the bytes of whatever / is, X is, 6 is, and 1 is. I don't want the byte value of hexadecimal 61. I want whatever that would actually be. Then you actually have to escape it. Hopefully this is making sense. I don't know. So now it's telling it it's escaping out that \, so it's saying it actually is the string \x61, and you can see that by if you do and underscore just means use whatever the last evaluated statement was, which would be the thing above it, and we'll print out the B, and it's going to print out a bunch of integers. So it's going to print out \x61. So even though we see two backslashes, one of them is actually just an escape character to tell us it's not B \x61, which would just be the byte value A. It's actually \x. So it's actually the array of byte values for these four. So again, like, I don't know, maybe I made it worse. Maybe I didn't explain it well at all. But basically, I just wanted to say, like, I don't know. For me, it was confusing as hell. It took quite a while before it wasn't confusing as hell. And I've answered a lot of questions for people, like, on, forums and stuff. And they seem to be confused by it. So, like, just kind of accept it and don't feel bad about it. And just treat it as part of the learning process. And eventually, it'll make more sense. But anyway, since we are doing a compare here, we'll actually change that back from, right now it's in bytes and we want it in string, so we'll decode it. And ideally, I guess if you wanted to be pedantic, you would write UTF-8. I think that's the default and not ASCII, but I'm honestly not sure. But see, now it's true. And then I'm gonna actually rename it since I named it 01 like a dum-dum. 01. And now we can move on to challenge 2. So now we are doing or XORing two hex strings together. So if you're not familiar with XOR, it's basically just an operation done on, it's a binary operation done on bits. So if you have your binaries, your zeros and ones, if you're comparing two bits and they have the same value, then you output a 0. If they have different values, you'd output a 1. So if you're comparing 1 and 0, you get a 1. If you're comparing a 1, 1, or a 0 to, a 1 to a 1 or a 0 to 0, then you're outputting a 0. And cryptography is basically all XORing practically. I mean, it's not, but like you XOR a ton. So like if you're completely unfamiliar with XOR, like I'd recommend watching some like Khan Academy or some like YouTube videos or something, because like you need to learn, love, and know XOR because you're going to use it a ton. So this time we're going to take these hex strings, so we'll call it x1 and x2. Also, I apologize for my voice. I'm actually sick, and I should, I mean, if this were going to be any good, I'd like wait and do it. But again, like I said, no one's watching this, and I just want to put something out so that I can stop beating myself up. We want that to be the answer, so we'll do just like last time. We'll do an F string, and we'll print whether or not. Oh, I need to make a result. Result. And result. We'll print out result. Result equals XOR hex 1 and hex 2. So like you see, I'm writing everything out before I actually make it. I feel like that's a pretty good way when you're starting out to like do things. It kind of helps you just get in the habit of doing better at like more kind of like the clean code practices where your functions just do one thing. You don't end up with like just a long, script full of like spaghetti code. And this probably isn't the best example because I'm just doing one thing, but like if you were going to do several things at once, you could still just go ahead and write it out. And if you're picking good names for your functions, you kind of, the way you would logically kind of write everything out ends up most of the time being like in those like specific little steps. So it's just a good way to like end up doing that, which is a good habit to develop anyway. So again, I said I was going to do everything, or I try and do everything in bytes and bytes, but again, just for this one, I'm going to do strings, and this time we'll even output a string, which I don't know why I'm doing it this way this time, but it just sort of makes sense in my head. So it specifically says it wants to take 2 equal length strings. So because we're good coders, we're going to put some error checking in just because it'll be fun. So the length of A does not equal length of B. We will raise an error. Input strings not equal length. And now, so I know like in the last one, we checked specifically to make sure they were hex strings. And this one we're not going to, because we're going to actually kind of do it in a way to kill 2 birds with 1 stone. So whenever you XOR anything, it needs, like if you use the XOR operator, and so in Python that's the caret, which might be confusing depending on what you've learned in the past. It's not exponentiation. But Python XORs integers, so you need it to be in integer form. So we're going to convert our hexadecimal strings using the built-in int function, and so we're going to convert the hex string, which is base 16. So you can convert any string, whatever base it is, if it is the correct format, into an integer, and then we're going to XOR it with the other integer. And what'll happen here is you'll see if you try and convert something, so we'll say like AG, which is not valid hex, into hexadecimal, it'll raise the error for you, so we don't actually need to write an error. So we're going to input those 2 strings, or convert those 2 strings, XOR them to integers, XOR them together, and what we're going to get back is an integer. But since for whatever reason I decided I wanted to output a string, we need to convert that integer back into a hexadecimal string. So we're going to use the built-in hex function, but you'll see here, like if we do hex, is that 97? You see we get an OX in the front of it. And since we want it to just be in this format, we need to get rid of that. So we'll use the slicing, and we'll start the string at the second character and go to the end. So now, save this. This should work. We're inputting these 2 hex strings, we're converting them to integers, we're XORing them together, and then we're converting it back into a string. And then we're going to compare that to what they want us to have. And we'll see if we get it right. So we got none result. Because I did not actually return it. So if you don't return anything, Python just returns none. There we go. So now we can go on to challenge 3. And this is where it starts to get interesting, if I remember right. Single byte XOR. Yeah. So what they want us to do here is we have this hex encoded string, and it was some piece of English, and it was XORed by a single byte. And when they say single byte, it just means like, do they even just explain that? No. It's just repeating over and over. So like if somehow I was going to XOR that, let me do it in text like, well, that's not, whatever, doesn't matter. If I were going to XOR this and I wanted to XOR it versus like just some single character, like it basically just, they're just making that the whole thing, that because they have to match up. So that's what's going on here. So I'm going to kind of do this. Well, so first off, this Etoian Sherdlu is a reference to the fact that English letter frequencies. So like E is the most popular English language, or the most popular letter in the English language. T is the second most popular, A is the third, and so on. So these are like the 12 most popular characters. So like kind of the straightforward sort of logical way to do this challenge would be, we know that this is the ciphertext, we'll just call it ciphertext of some message that was XORed by a single character. So we could just brute force it. We would XOR it back with all possible characters. And then we'll have a list of all of them. We have a list of strings of, various, they're all going to be gibberish but one. But then what we would do then is use letter frequencies to figure out which one is most likely English. Like, so for example, this ugly string here I made, which is clearly just gibberish, but like you could actually programmatically tell that it's not, that it is gibberish. There's E's the most popular letter. There's no E's in here. We're going to have way too many J's, like, that kind of thing. I'm actually going to do it a little bit different because I think it'll help explain it'll help make one of the later challenges, it'll help understand it more. And also, I guess, because that's sort of how I learned to do it in one of my crypto classes in uni. And also because I imagine the way most people do it is the way I just explained it, because it's kind of the way that makes the most logical sense. And I don't know, it's always good to like try and understand something multiple different ways, because it just helps it stick in your brain, and it helps you just understand it more. So if somehow someone's watching this and they get how the other way works, maybe like this new way, or it's not new, but it's a little bit different, will help, I don't know, explain some other things later on. What we're actually going to do here is I'm going to count the letter frequencies in the ciphertext and make a normalized vector of that and compare it to all the possible frequencies that you would get for the letter frequency vector XORed under specific keys, which might sound really confusing, and especially because I started using math terms, and if math's going to freak you out, like, don't worry at all. Like, it's really not that complicated, and hopefully I can explain it well enough that it makes sense. But either way, it'll be like something different. So also one thing I want to do here is, since like I said, we're going to be XORing like constantly all the time, a ton, I'm going to go ahead and instead of like kind of the good way, probably someone with a lot of the other videos I'm sure that do this is going to like teach you stuff, is like, oh, well, we already wrote an XOR function in the previous challenge, so let's reuse that XOR function and, for this challenge. and all the challenges for on. But since, like I said, we're going to be doing a ton of XORing, we're actually going to make a separate, more robust XOR function that will be able to handle multiple different things. So we're going to make a utils directory, and then we'll make a utils file. Oops. Why can I not type today? It's the pressure of the camera. And we're going to put our dedicated XOR function in here. And we're going to do a few things. So we're going to use args and kwargs, which, if you aren't familiar with what that is, that basically args just means we can have a variable length of inputs. So if most of the time we're going to be just XORing two things together, but I don't know if we'll do it in these challenges. Definitely not set one, but I'm not sure about later on. But there are times when you're XORing like multiple things together. So this is a way, like, instead of having, like, if you wanted to have a function that took 2 and then one that took 3, like, you would, instead of having to write a function for each one of those, you could just use this args, and it's just means it's a variable length of functions. Okay. And kwargs is like a variable length, like key value dictionary. You can basically, so like we can have values. So like if you've ever seen, well, here, so like for example, we want to be able to take this function and have it XOR variable length strings, just how we're going to be doing in this challenge, where we're going to have a long string and then we want to XOR it with just a single character, but we want to make it so that the strings end up being equal length. And we could either do that by having logic that like makes it, well, so there's two different things here. We're going to do it without using logic to like actually physically make each string the same length, because that just is more complicated. But we also want to have a way to say, maybe I only want it to be as long as the shortest string, or I want it to be as long as the longest string, or maybe I only want it to be 6 bytes long, regardless of how long the strings are. So if we have like a value, so like it'd be the same. What I'm trying to say is, like, say we're going to XOR, this would be in our code somewhere. We're going to XOR, and we're going to XOR A against B, and we want to be able to specify some value. So this would be the key values that are going to be in kwargs. Hopefully that made sense. So what we want to be able to do is have a length parameter or variable, and what we're doing here is this pop is, it's going to take the length indice from this dictionary. If it exists, it'll take whatever it is and set it to length. If it doesn't exist, we're saying the default value is max. So if you don't ever pass in anything, it's automatically, there's still going to be one set, which would be the same as if we just did this as, right? So like we could write the function the same way. But this way, by using kwargs, we set ourselves up with the ability to easily be able to add to the function later on. I don't know if we'll want to or need to, but like we'll be able to if we can. So it's just kind of a way to, like, I don't know, set your code up to be more flexible, and you run into less problems later on. So we're going to have this length parameter, and we're going to check to see if it is an integer. And if it is, we'll just keep it as an integer, or length, we'll set it. So the default is max. If it's not, it's going to grab it. And we're setting it to itself again anyway, because I want to be able to do a little bit of error checking. So if the length is max, we want the length then to be, oh, so actually we need to set up. So let's call it strings equals S for S in arms. So this is, we're using list comprehension here. For every argument we give it, we're going to create an array that is, or a list that is all those arguments. So our input strings are now going to be in a list we're calling strings. And so if the max, we want the length to be whatever the longest string is. So we'll say the max of length S for S in strings. And then we'll do the same thing for if we say minimum. And then now we can have error checking. So if it's not max, if it's not min, and it's not an integer, we will raise. And let's say invalid value for length parameter. I cannot spell, so. Now we actually have to get down to the business of XORing. And like I said, since we're not going to actually physically make each string the same, what I'm going to do is write a little inner function here. Indices, index. I'll write this out and then I'll explain it. So for each string, strings, we want to XOR it with B. Oh, no, we don't. We want to XOR B. XOR equals the index modulo the length of the string. There. Makes sense. And we'll return. Okay. So what we're doing here is, if you're not familiar with this, it's the modulo operator. So basically what it does, and if you know any other languages, or you probably, this is one of the earlier things they teach you kind of in coding, because you end up using it a lot, but like 7 modulo 5 is going to be 2. And kind of the way to think about that is, if you divide 7 by 5, you get 2 left over. So it'll actually turn that into 2. So what we're doing here is, this is kind of our way to loop back around the string. So if we have 2 strings, one's 10 bytes long and the other one's 7 bytes long, our program doesn't shit the bed when we get to byte 8, because the one string is only 7 bytes. It'll, so here, if we're on index 7, but our thing's only 5 long, it'll loop itself back around and do 2. And same, that's why we don't need like anything XORed with 1. So like if we just give it a single byte, anything XORed with 1 is 0. It's just constantly going to keep using that one single byte because index 0. And the reason we set this to B at the start is anything XORed with 0 is always 0. And then corollary to that is anything XORed with itself is always 0, which makes sense if you look at it, the binary. But so the first time through the loop, we want to grab the first one. So we're XORing 0 with whatever that position is in the first string. So that'll give us the first value. And then the next time through the loop, we're XORing the first one with that same position in the second one. And then that'll be the combined value. And so that's a way to like get them all. And then what we can do is use our list comprehension. So for I in however long length is, we want to XOR this is kind of how I write list comprehensions, because I know it was kind of confusing to me to start. So I sort of do the loop first, but so we're saying we're going to loop over however long the range is, and we're going to XOR all those indices together, and it's going to create a list with each one of those values. But like I said, I want to do bytes in, bytes out, so we want to return a byte value. So if we wrap that in bytes, it'll return a byte string. One way to let's do here. So like if we had an index or a list that was like, say the value is 97. So this is just going to be A, B, and C when we're done. But so it's a list of integers, and we can convert it to a byte string by just inputting that into the bytes function, and then we get our byte string. So now it will return bytes, which is what we want. And ideally I should test this. So let's actually, I'll just quickly, we'll test. So we're going to utils import. I'll import it as XOR2, so there's no conflict. And I'm just going to do it, just run this real quick to check it, just to make sure it works, because nothing ever works on the first try. So I'm sure there's some kind of mistakes I've made in that XOR function. Oh, wait, no. Oh, okay, that's what I have. So I want to import XOR, but I want to name it XOR2. Okay, unsupported operand. We cannot XOR an integer and a string, so somehow in here I am XORing an integer and a string. But I'm not sure. Module length x. S4, S, and arg. So we got an array full of strings. We're saying an index. XOR index is I. So for string in strings, B XOR S index modulo length of S. I'm not sure why. How is it getting a string value? Oh, I'm so dumb. Because this is the joys you get when you just sit down and do one thing and all take. But I mean, I don't know, it's part of programming, so I don't know. Maybe this somehow is helpful. This is also a problem you run into when you end up just like reusing other code to like try and test stuff, and probably shouldn't even do it because it's just a bad. Since these are still strings, I'm actually inputting strings, and we don't have any kind of checking or anything in our function to make sure we're actually working on bytes. So what we would need to do is convert these 2 bytes. And now, okay, but since we outputted bytes, it's still not going to work. But we can tell by looking at it, that's what it's supposed to be, I believe. Let's go ahead and we want to. Okay, wait. Else the kid don't play. Result is in bytes, so we decoded it. So now it should. Oh, so it's a string, but it's not a hex string. Whatever. I'm not. Well, now I'm gonna be all anal about it. So wait. So it's a string, and we want to convert a string into hexadecimal. I don't want to import like bin ASCII or anything like that. So just, yeah, I mean, you can take my word for it. It wouldn't have worked out like that if it wasn't. And then now we have to go back and take out all the crap. So yeah, I don't know, probably don't do that, but at least now we know it works. So now that we have our nice XORing function, we can go back and take our hex encoded string. Actually, so what I'm going to do, I'm going to pause this real quick because obviously I don't know the values off the top of my head, and so I'm going to Google those to look them up, and then I'll put it in like a dictionary so it's like an easier format to use, and I doubt anyone wants to watch me Google things and slowly type in 26 characters. So I'm going to pause and I'll be right back. Okay, I'm back. I've actually been back. I was rambling for a while and forgot to unpause it. So now I can say whatever it is I said. So I managed to find some English letter frequencies, and got one with the space, which actually will be really helpful. Normally when you see them, like the digits, a lot of them were like taking just words from the dictionary, like the analyzed dictionary, but I found one where they actually analyzed, like, I don't know, all the works of English text or something like that. Anyway, so this is what the frequencies are. So what I'm going to do is try and explain it. I got my little thingy here, and I'm going to like try and hopefully I do a good job explaining this, because if I can, then I think it'll really help for one of the later challenges in this set, as like it'll make more sense why what works. Anyway, so what we're going to do is we're going to create a vector of the frequencies where the index in that vector is the frequency of the corresponding letter. So like we're going to do it for all 256 byte values. So like byte value 0 would be a 0 because it's not even a printable character. Same for like the first few, and we'll just go on up, and then like we see we start looking at the letters, and we're just gonna convert everything to lowercase. So like A, we've already shown is value 97. So the 97th position in this array will have 0.0655 as our value. And then the next position is the value for B. Erase that. And then, then we'll add the value for C, and yada, 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 all the way back once you get past 127, because ASCII is just 0 to 127. Once you get past that, we're not even into the printable characters anymore, so it's just going to be all zeros again. And this is like a vector representing the frequencies of what English language would be. And what we're going to do, like I said, is we're going to analyze the frequencies of our ciphertext. Let's just go ahead and look at it. And I did this. This is one of the things I did earlier while I was rambling with the pause button still on. Just type it in again. So our string is this beautiful set of gibberish. So we can see like we have x1b, which isn't even a printable character, and then a bunch of sevens, it looks like, another x1b, another 7. So what we would actually do is we're going to count up. Oh, great, I lost my. Okay, it's back. What we're going to do is we're going to create a vector with the values of this. So like we'll call that vector W. And I don't actually know the position, so like x1b would be, what is that, 27, I think. 7, I know 7 from trying to do it earlier is 55. But so let's say that like this isn't actually going to line up, but I'm just going to use it. So say our ciphertext did have some values where it was like, oh, we had 0.01% ends up in byte 0, and we have some zeros, and say we end up with 0.064, and then, blah, 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 blah. That's our array. Now, if what we were comparing, like if we had an actual piece of English text and we compared, you know what, I'll go ahead and, it doesn't matter. Well, just to make it look nicer, I'll go ahead and sort of make it line up with blah, blah. And then, let's see, that doesn't line up. Whatever. If it did match up, the vectors would kind of look the same, right? Because we know this isn't going to be English because these frequencies are all, well, non-English. A lot of them are even not printable characters, and there's numbers and all that. But if what we do is, like how I said, we're going to compare that to every possible way you could have XOR'd the original vector. So we're going to have a list of all the possible ways of all the vectors. So V0 would be the result of XORing all the values by 0, which we know anything XORed by 0 itself. So V0 is actually just going to be that same English. Let's go ahead and just do it. That's V0. It's going to be that same English one because nothing actually changed when we XOR that. So if you had a piece of text and you were going to be encrypt air quotes, you can't see it, but I'm doing it, air quotes, and send it to somebody, don't XOR it with 0 because you're just going to send them the actual plain text. But we're going to have a list of all the possible ways. So V1 would be what it looks like when we encrypt or when we XOR everything with 1, which I can actually do that one. 97 XORed with 1 would be 96. So in the 96th position, we would have 0.0655. And then 98 XORed with 1 would be 99. So what would end up 97 being what would have been 96, which we know is 0, I think. Whatever. And then 90, so this was 98 XORed with 1 is, that would be 99. So 99 XORed with 1 would be 98. And then 0.027 would be our 99 position. And then, whatever they all are, blah. We'd still have zeros at the end. Blah, blah, blah. Anyway, and then we're going to do that for V sub 2, V sub 3, all the way down to V sub 255. And what we're going to do is you can think of it as we're going to compare W with every single one of those, and we're going to see which one it matches up most closely with. And the way we're going to compare that is by taking the dot product, which, again, if you don't know what that is, don't freak out. Dot product's really simple. If you have two vectors, we'll just say vector A equals 2, 4, 6, and vector B equals 1, 3, 5. You get the dot product. The dot product of A dot B is you multiply the same positions and you add them all together. So 2 times 1 is 2, added by 4 times 3 is 12, added by 6 times 5 is 30. So you add all that together and you get 44. So what's going to happen is, let me erase all this. What's going to happen is if we take the dot product of W with every single one of these vectors here, the one with the highest value is going to be the one that most closely aligns with itself. And this kind of is the key takeaway I want you to get and hopefully explain well. If we take vector 0 and we were to XOR it, let's say we had in our list of all, our list of all the vectors, we'll put vector 0 is in there as well. If we take vector 0 and XOR it with, where's my thing not showing up, with every vector in there, here we go. The one that's going to have the highest value is when we multiply V0 with itself. And if you look at it, the reason why is if we were to XOR all these things together, 655.0. Oh, it's 0127. 0.0227. The point where it's a 5.5. When when the vector equals itself, that's when you get the max value, because like if you look at it, we're multiplying the zeros together with each other. So like those are all going to be 0. The biggest values we're multiplying with the biggest value. So like the biggest value in the vector is getting multiplied by the biggest value in the next vector because it's the same vector. But like when you look at it, if we're using W's, like since W isn't actually going to exactly match one of these, but it'll be similar to one of them. So it's the same kind of thing. The biggest value in what our actual English language shifted or transformed by whatever we XORed it with should be the letter E, right? Like, because E is the most popular language. So, 10% of all the characters we expect to be E. So when we XOR it by, like if we look here, like it looks like maybe the most popular one is like there's a lot of 7s. So whatever E is normally is probably what 7 is. But what's going to happen is the biggest value E is going to get multiplied by the biggest value in here. And so the bigs get multiplied by the bigs and the smalls get multiplied by the smalls when their frequencies are similar. And that will give us the biggest value. Otherwise, you end up, like, I just know from doing this, like if V0 multiplied by some random one that's not itself is usually somewhere in the range of like I think it's like 0.25 to like 0.33. And then when it's multiplied by itself, I think it's like 0.6. It's either 6.6 or 6.8. But like, it's the only one that's like bigger than 0.3 something. So like it's like far and away bigger. So the kind of same thing is going to happen when we take the frequency. I'm writing it where I'm not even showing you. Hopefully I wasn't doing that very long. Whatever, do it badly. That's kind of my philosophy that I try and do to like help me get over like when I'm stuck with perfectionism, is like just do something badly. And that's my goal, then oftentimes it helps me do it because like what do I care, I'm trying to do it badly. But then also like you end up finding out like your badly it doesn't end up being that bad, and then you actually completed something. But I don't know, we might actually be in the realm of of badly here. But anyway, so like it's going to be head and shoulders above the rest. So that's kind of like the key concept here, and the key thing I want you to take away, because this is what's going to help later on, is whenever the vectors are the same, is when it's going to be its biggest value. So like the dot product of our W with whichever one is mostly similar to the W is going to be far and away the bigger value. So, and that's going to end up like how I explained, because like we end up multiplying whatever the most frequent letter is here with the most frequent one that it was under its transformation all the way down the line. So hopefully that makes sense. And if not, well, I don't know. I'm sorry. Feel free to ask questions. Leave a comment below. Smash the like button. Subscribe. Blah, blah, blah. Anyway, so let's go back to now actually writing this. So, so we have our encoded string. So we'll actually start calling it our ciphertext. And I'm going to go ahead and put it into bytes. Ciphertext. And then what do I want to do? Well, our main goal here is to evaluate each output and choose the one with the best score. Oh, here we go. find the key to crypto message. So we want to find the key. So we are going to say the key is equal to get single byte XOR. I'm going to give the ciphertext. And then let's go ahead and print out the key so we know what it was. And we'll say the key is key. And then we want to, let's get our plain text back. So our plain text is going to be the result of XORing our ciphertext with the key. And we'll do that by importing from utils. We're going to import our XOR function that we wrote. And so we're going to print the key, and then we'll print the plain text. So now I want to write the get single byte XOR function. So and we're going to take bytes because we're always going to try and take bytes, and we're going to return bytes. And so let's say we want to, how are we going to get this single byte XOR? So if we had a vector, our frequency vector for the actual ciphertext, and we multiplied it by all the vectors we can make by transforming them under the XOR operation over the bytes, we will get a whole bunch of scores. So let's, well, a whole bunch of values. We'll get all the dot product values, but let's just call it scores because it's an easier thing. So we want to get, let's call it get vector scores, and we'll pass it the ciphertext. That's how we'll get it. And then we'll now have, if we have a list of all the possible scores, we want the key is going to be the one that is the best score. And the dot product is going to be all in integers. So I'm going to do it in 2 lines. So we want the index of the max value contained in scores. So the array scores will be an array of all the dot products we get from XORing it over each of the values. And we want the index where the score is the highest. And that's going to be an integer. So what we're going to want to do is return the byte value. So now we need to write the function to get all the scores. So get vector scores. We're going to pass it a ciphertext in bytes, and we'll be returning the list that is all the dot product values. So we need to create all the vectors. So let's say frequency will get vectors, and we don't need to pass it anything because we'll put that dictionary in that function. And then we have our W vector, which is actually going to be the vector that's the frequency of our ciphertext. So we could call it get actually let's call it get occurrence vector. It'll be a vector that's the number of occurrences of the bytes. So we're going to pass it that, and then we are going to take we're going to return a list, and we want that list to be the dot product of our ciphertext occurrence vector with each vector in, or v for v in frequency vectors. There we go. So for each vector in this frequency vectors, which will be the list of all the vectors, where the index in that list is what they're transformed under x or by, we need to get the count of our vector, the ciphertext vector, and then we're going to return the dot product of all of that. So let me go ahead and write the dot product, which, as I said, is pretty simple in that the dot product, we're going to take two vectors and they're going to be in lists. And the dot product takes two vectors and returns an int. And what it is it is, it's going to return the sum. I'm going to use this here. So we'll say that for I and j in zip. So what zip does is it takes two lists and it, I'm not sure what that structure is. Enumerable, iterable, I don't know. Basically what you can think it is, it takes two lists and it like zips, I'm doing air quotes again, zips them together, or it just kind of like lines them up. Like you can think of it as lines up on top of each other, one over the other, and then, you know, I will be whatever the, so the, oops, this is AB, not IJ. So the element in A that we're on will be I, and the element in B that we're on will be J, and it like lines them up, and we're going to multiply I times J. So we're zipping the lists together. We're going to multiply each element with the corresponding element. That'll give us a list of integer values, and we want to sum all those up and return that, and that is the dot product. So we've done our frequency, or we haven't done our frequency vector, and we haven't done our occurrence vector. So let's write our occurrence vector. And what we're doing is we're taking bytes and we are returning a list. Maybe I should use tuples for vectors. I don't know. Haven't really done any vector stuff in Python, so I'm not really kind of sure what the sort of best practice is or what most people do. They probably end up importing like NumPy or something, I would imagine. So we need to know how long the list is, because we need to normalize it to get the percentage, right? So we need to know like how many of letter A's are there, but we have to divide it by the total size of the list to get the percentage of A's. So then we'll just, our final vector is, I'm just calling it W. I'm capitalizing because like in math, typically a vector is like bolded or capitaled. And then I'm calling it W because like when I learned how to do it, I don't know, we just called this vector W. It's like completely arbitrary. But anyway, it's going to be, we're going to start out with a vector of all zeros, 256 of them. And then for each byte in A, we are going to add 1 to that position. So if the byte value is 97, and when you iterate over a byte string, it gives you the byte in integers, so which is why we can just use it directly in this list. So if we had the letter, what we say, X was 120, if it was the byte value corresponding to X, it'd be 120. So position 120 in our array, we're going to add a 1 to it because we've seen 1. Every time we're going to add 1. And then we would need to go back through and divide by the size of the array, divide each one by the size of the array. But I'm just going to go ahead and, instead of going back through and dividing everything, we're we're going to update by 1 divided by the size, because 1 divided by the size is the percent value for each occurrence of a character. So we'll just do it that way. Hopefully that makes sense. And then we're going to return RW. So we're taking we're taking a byte string, and we're going to return a list, and that list is the vector. That is the number of occurrences of each byte in that string. Okay, that looks right. So now the only thing we have left is we need to make this frequency vector. So we need to, or vectors. So we need to create the array of 256 vectors that are the transformations of the original vector. So maybe instead of having it in a dictionary, I should have just did one long array. Let's just go ahead and we'll make our and I know this might be something I should have pulled out and like put in its own like put in a separate module or something, but let's just go ahead and do it this way. So here's our English frequencies. And if I had, so one of the advantages of pulling it out is like then you could abstract it a little more, and instead of having to write a different function for, like say we started working on French texts, we could have a dictionary that was the values for the French, and we could have all the different dictionaries, and we could just tell it which one we wanted to use, but we don't need to do anything that fancy here. So let's go ahead and just try and convert this into what we want it to be. So if we know we're going to have our final array is going to be an array that, okay, so each, generally you do it without spaces, I'm not sure. Each array is going to be 256 long, and there's going to be 256 of them. And then I'm using the underscores because that's just kind of the convention when you iterate on something and you don't actually need the variable. You just use the underscore. That's kind of what I've seen people do. So then now we want to, we can just do it all at once. So we're going to say for key value in English frequencies items. So if you want to iterate over the keys and values in a Python dictionary, you can do it like this if you just put items. So it's going to iterate over it, and it'll get us the key, which is this first part, and then we'll have the value for that. So what we can do then is now for each row, so like we want to get what A is, and we want to put this value into each of the 256 vectors where it would go in that vector. So like if we were to XOR by the value 30, this value here will go into whatever position of the 30th list in there on the position of what 97 XORed by 30 would be. So I don't know, hopefully that made sense. But we'll do it like so. For row, we're going to go through each row, and we're going to say the frequency vector of that row. So K, I don't know if it gives us, when it goes through the dictionary, like when you iterate over a byte string in a list, it gives you an integer, but I don't know if it automatically converts the key in a dictionary if it's a byte string, or I guess it wouldn't. It would just it'd give you the byte string. So we want, because we're going to update that position in the array, so we need it to be, we need to XOR what that is. So we're XORing, like say A, which is 97. We're going to XOR it with whichever row we're on, and that index in that vector will be equal to the value. And so it'll do that for each return. Okay, now hopefully that kind of makes sense. And like, I don't know, if not, and maybe I'm just explain it bad, but with a lot of stuff, I feel like people, and I used to I was a tutor, math tutor in college and stuff. So I've done a lot of tutoring and helping people. And one thing I always kind of see the way people think, which isn't actually how you learn, and you shouldn't expect yourself to learn this way, is like thinking you're gonna understand it just because you've seen it once. Especially with cryptography. I'm going to go off on a little side rant soapbox here, but especially with cryptography, I see it all the time where, because people don't generally have a strong math background, but they get into hacking and CTFs, and then they want to start doing crypto, and then they encounter math papers, and it's pretty intimidating, because I mean it literally is a different language. Anyone tells you math isn't different languages, kidding themselves or you, which is why people need to give themselves a lot more patience when they're learning math, because not only are in cryptography, not only are you learning concepts and ideas that are difficult in their own right that would take a while to learn, you're learning it in a completely new language. No one would shit on you, and you wouldn't shit on yourself if you were trying to learn how to I don't know, do engineering in Swahili, because it's all in a completely different language. You'd be like, man, this is freaking hard. I gotta do this in Swahili, damn. Everyone would be like, oh man, damn, that's rough. But no one gives themselves that same compassion or same leeway when it comes to math. But you should, because all that symbols and all that stuff, it's a different language. And then on top of that, people think that I have a degree in math. I have a undergraduate maths degree, and I've done a whole bunch of crypto. My emphasis was on crypto for my degree, and I do one of these harder cryptography challenges, and I find a math paper, and I have to read that paper it depends on how hard it is, but sometimes a dozen times before it starts to make sense. And people are out here thinking that everyone who knows how to do this stuff is just reading the math paper and it clicks, and there are people who are like that, but they also are either really, 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 really smart, or they also just have a shit ton of experience. But my original point basically was, before I started rambling, was that I get the distinct impression that people feel if they don't get it the first time, or it doesn't stick, or it doesn't make sense, and they have to go over it again or struggle with it for a while in order to understand it, that they either think it's too hard for them, or they're too dumb to do it, or any of that. And that's not the case. All the stuff I've learned, I can't tell you how many times I pause videos and have to go back and pause it and go back and pause, and it doesn't make sense. And now it might not be the case for this video, because I'm probably doing a shit job of explaining everything, but if it kind of makes sense and it slips away and it doesn't make sense, and my code, you don't quite understand the code, there ain't nothing wrong with going back and looking at it again and trying to listen to what I said again, which is also one of the reasons I tried to kind of explain this differently than you normally see it, because one of the ways that's very helpful to learn is the same concept explained multiple different ways. A lot of times with these crypto challenges, I'll find a math paper that tells me how to do it, and I don't get it at all, but I get a little bit of it. But then I find someone else who wrote a math paper that's basically the same thing, and they explain some other little part of it a little bit differently, and that sort of makes it make a little more sense. And you end up piecing together concepts from 3 different papers and 4 different textbooks, and then you finally end up getting it. And I realize as I'm explaining all this, none of that makes doing cryptography or any of this glamorous. But I don't know, if you hate math and you hate programming and you hate all this stuff anyway, not that anyone made it this far in this video, but no one is here anyway. So I don't know. It's fun. What I'm trying to say is be kind to yourself. Give yourself way more credit. Don't feel bad in the slightest if stuff's confusing, even if someone way smarter and way better at this is explaining it to you. Like, ain't nothing wrong with like struggling with the code and going back and doing it all multiple times before it makes sense. That doesn't mean you don't have the aptitude for it. Doesn't mean you're not smart enough for it. Doesn't mean anything other than you're exactly like everyone else who had to do the exact same thing when they were learning. Anyway, I think this is all, but as we've seen, there is literally no chance that this runs on the first try because it's way too long and I probably made way too errors. But that is kind of like typically how I would write out my program, is like breaking it down to little pieces and then writing it in the larger sense and then going back and writing any piece. So I don't know, let's moment of truth. What is this, challenge 3? W is not defined, line 26. So I have lowercase w instead of an uppercase w. The other thing about not using an IDE is when you have to go back through, oh shit, second try worked. You end up getting better at like reading that, which I don't know. I probably just tell myself is like, oh, I'm getting practice like debugging, when really I'm just wasting my time by not using an IDE. Anyway, so yeah, boom, worked. So we see that our key here was the letter X, and that string they gave us when decrypted gives us that. So yeah, I'm quite happy with that, I guess. I don't know. Here's where like I would like, this would all fall off the rails for me if I wasn't just trying to do this in one shot. Is like, I don't generally, it just does not seem, I don't know, it seems kind of ugly to me. Like, I don't like the fact that I know we're going to have to be reusing some of this stuff later on, and it's not really conducive to being reused. And like, I don't know, what should I put in a class, and I should rewrite some of these, and then I just go over it a whole bunch of times, and then I end up just getting sick of it, and nothing ever gets done. But we're way too far into this, and we're only challenge 4. Maybe I should break these up into multiple videos, but nah. So what is number 4? Oh yeah, see, so we want to reuse our code. So this, oh, that one's shorter. So let's go ahead, we're gonna need this file. And I know that we end up having a lot of other files. So let's go ahead and make a separate directory. To put all these text files in, and this is challenge 4 text. Does it end with a new line or not? Okay. So basically, one of these was XORed by single key, and I'm assuming all the rest are just random. I don't know. And we need to find which one it is. So basically, we're going to do the exact same thing we did in challenge 3, but we're going to do it for every single one of those vectors, or every single one of these ciphertext, air quotes, because only one of them is actually ciphertext. And then we want the one that most looks like English, which would actually have been easier had I done it the other way, but it won't change anything. What we'll basically do is we'll get, so we did, we'll just reuse this function, our vector scores. We'll get the vector scores for every one of these, and the one with the highest score is going to be the one that was most likely to have been English text encrypted under a key, and the rest, if they are random, will all just be values in the 0.25 to 0.35 range. So yeah, we're pretty much just exactly reusing challenge 3 code. So let's just go ahead and, again, this will drive me nuts, but let's just import challenge 3 and we'll reuse some of these functions. So basically what we want to do, let me write it out like I would here. So we want our ciphertext to be, we're going to parse our input. And then our winner will be the one that has, well, our winner will be find XORed ciphertext, and we'll give it the ciphertext. And then yeah, so let's do the parse input first. That is the easiest one. So with open file name as f. It's just kind of the general syntax you want to use for files. If you do it with the with open, it handles all the closing for you when you're done with it, so you're not leaving memory leaks and stuff. There's a lot of tutorials and stuff you'll see, f equals f dot open or whatever. I forget how it goes, but don't do it that way, because then you have to close it. You have to remember to do close. This way you can just I'm done. So our ciphertexts are going to be what we get when we read the file, and it's all, each one's on its own line. So we'll just split it. We'll split it on the new line. And since we always end up working in bytes, doing everything to bytes, we use list comprehension to write. These are all CTs right now is going to be a list of hex strings. So we want to convert all those. We want a list of byte strings. So we'll say for CT in CTs, bytes, hex, ciphertext. Now it is a list of byte values. We'll return that. So now we need to write our sort CT. So we're taking a list and we're going to return bytes. I'm just trying to think how to do this. Basically we're gonna do the exact same thing we did here. So I'm trying to see, if we just reuse get vector scores for each ciphertext in our list of ciphertexts, what it's going to return is the dot product of all those. And we want the largest one, but we need to keep, oh no we don't. Okay, yeah, we just want the largest one. So we could just do, actually, let's return, I'll leave it bytes on. And one thing is, whatever you put here doesn't actually matter, unless you're using what do they call it, a linter or whatever. And then or if I use this as an IDE, then it would be oh, you're not returning bytes and you've said you want to return bytes. But the actual Python interpreter, when you compile it and run it over, it doesn't, there's no type checking, so it doesn't actually matter. But don't just write random crap and stick it there anyway. So let's say we'll do it this way. We could probably write it. Well, first off, we know we're going to want to have export CTs, and we are taking. If we do it this way, it'll call that function for us. It'll call all those, and it'll just return a dot product. Okay, so if we just did, all right, I'll just write it out, and then I can always rewrite it to make it make more sense. So for ciphertext in ciphertext, we want to get the what is it called? We want to get the vector scores for that ciphertext. And then we want ultimately the one that has the best score for each. So if we just did, here, let's do it. Let's do it this way. Best ofs. All right, so for each score, we'll call this, or I'll write it out long ways to make it make sense, and I can always just shorten it. Our max score is going to equal the max scores. And then we could input into the best ofs a tuple that is max score and the ciphertext. And then when we're done, we could sort that array. We're going to use a lambda function, which lambda function, if you're not familiar, is basically just like an anonymous function. It's basically, there's no difference between it and any other function. It's just you're not giving it a name. Basically, that's it. I could write, I don't remember if you're supposed to have a space, but I don't think it matters. I could just write a separate function and stick that here, because the way sort works is it takes a function and that's how it sorts it. But so we're going to sort by, we're going to sort everything by the max score, and that will be, I always mix up ascending and descending. It'll be lowest first, so I believe we can just say reverse equals true. And if that's not the case, well, definitely not true. I think it's true. And then if we return the first element in that, we'll be returning a tuple that is the score and the ciphertext. Yeah. So we could actually just return the ciphertext, and then that will be, hey, this is the best one, although we won't know the key for it. So if we want the key, yeah, let's do it. I don't see it. I'm gonna get frustrated. So let's just not worry about it. So scores, but I do want, because I want to decrypt it, I want to know curiosity if it says anything. So let's get so let's get the key is the scores index. I should get the what am I doing? I should just get the max score. Okay. And then the key is the index of the max score. And then we'll sort it. We'll do the max score, the key, and the ciphertext in our tuple. And then we'll go ahead and just return it all so that in our main function, we're going to get whatever. I should rename that. It's not a good name. I should call it like XOR ciphertext or whatever. But we're going to get whichever one was the best. And then because I want to actually see what it says, let's go ahead and so let's just go ahead and print out whatever the winner is. And then we'll see its score too. And like I said, it should be around 0.66. And then you know what, just for giggles, let's see, because I want to show you guys, let's see what the first 20 scores are. And then that's, so our winner is, and then I want to know what the plain text was. And that is going to be our XOR of the winner and the key of the winner. And is it the key of the winner in bytes? No, it is an int. So I don't think that matters. Well, we'll find out when we run it. All right, so I believe this will work. And I don't like how long and ugly that function is, but let's see what errors we're going to get. Oh, ha. Challenge 4. No, oh, utils.utils. List object is not callable. Line 17 and find XOR CT. Oh, yeah, we're pending. Oh, sweet. So it's gonna take a little bit because right, it's got to go through every single one of those, and then it's. Oh, okay, yeah, I do need to make it a byte. But anyway, so our winner was this one right here. It was 0.066. And then values for everything else was, yeah, the next best value was 0.033. And then 33, and then even the 20th place one out of however many are in that. However many in that was even just already 0.027. So you can see like it's a pretty big spike. And we did, I should change this so that if we give it an int, you know what, I just want to check something. What happens if you do, you give it a byte string and say bytes. All right, nothing changes. So what we could do here is do, now this probably isn't good practice. Although we could, so if we gave it a single int, it would change it into a byte string, right? Because we're basically just doing like what was our key here? 53. So, oh, or does it? No, it would do. I think we'd want to do. It'd be the equivalent of doing that. Yeah. Well, I'm gonna try it and then I'll see what I'm saying. I don't think it'll work. Oh, I didn't even save that, I don't think. Oh, it did work. Right, no, it didn't. Yeah, because it XOR'd it with zeros. So that's what it did. It made. So I was just trying to think of a way. It'd be cool if we could change this function so that if we just gave it a single integer, it would automatically just convert it to a byte. so I thought I could do it like that. But I don't know, there probably is a simple way, and I don't know, I'll look for it later. I don't want to waste everyone, like anyone's watched this. I don't want to waste anyone's time with doing that now. So we'll just go ahead and convert this to bytes. Oh, and then we don't need to like print out the keys anymore. I just wanted to do that to show you. Huh. Why is it not? It's still XORing it with nothing. ZB15A. 1 or 2 bytes. Did I not change? I didn't save it. I'm not understanding that here. Let's try it in here. So let's XOR. Well, first off, what is 53? I want to say okay, it's just the letter number 5, so this is our ciphertext, and our key is number 5, and we're going to XOR ciphertext and the key. Yeah, why is it not doing it there? Max score, key, ciphertext. We're XORing the winner. I'll do it out. Maybe I'm just, I don't know, maybe I've just been doing this too long now. My brain's shutting down. So we know the key is winner 1, plain text equals winner 2, XOR text key. Object as no int length. Oh, because I didn't put I didn't make it a bytes value. Maybe I did it wrong when I was doing it the other way. I didn't put the square brackets in it. Yeah, that's must have been what I did. All right. So yeah, challenge 4 down. Challenge 5. Oh, this one. This one's gonna be super easy. So basically, our fancy XOR function already does what it wants us to do here. So see here, their key they're giving us is 3 characters long, and they want it to be long enough to be able to XOR everything. So this one should be super easy. Oops. So here we just have our stanza, and oh, they have single quotes, so we want to double quote it, and we'll put the line break in it. And then stanza. The answer, our key we know is ice. And we'll go ahead and already make it a byte string. And the answer should be this in hex. Put and then our result. So let's go ahead and make just do that. I don't know what happens to the /n if you do it on a byte string. Test equals blah blah /n blah blah. Is that going to be 2 lines or 1? Let's. Oh, I gotta encode it. Decode. Oh, okay. It keeps it as /n. Cool. So we can just go ahead and already make those bytes, and our result is going to be what we get when we XOR the stanza with the key, and that's going to be in bytes, and we want to see it in hex. How do you go from bytes to hex? Well, one way I know you can do it is import bin ASCII, and you can do bin ASCII hexlify. Pretty sure this takes bytes. If not, we'll get an error and we'll find out. So let's do our goofy test here. Oh yeah, but I want. Here, let's check this. Import bin ASCII dot hexify. Let's hexify test. Oh, all right. But it does put it in bytes, so we want. Oh, we know it gives it in. Decode. That's going to come out in bytes, and we want to make it hex or string. So now we can check answer equals result, and then we'll print out the result just to make sure. Yay! So see, that was easy because we'd already done that one function. Now next challenge, I'm pretty sure is the one. Yeah, okay. So let's go ahead and. Okay, so this is the one where I wanted to explain why what's going to happen works. So. Okay, we do have another file. And it is all. So we want to, in resources, we want to challenge 6 text. Get rid of that last new line. So, and this is base 64. Okay. So what we're going to do here is basically they had some long piece of text and they encrypted it under some key, like how the last challenge was text encrypted under ICE. So they're encrypting it under some key. We don't know what the key is. and we don't know how long the key is, and they want us to break this. And we're going to be able to do that. They tell us how to do it, the way they suggest it. We're going to do it a little bit different. And so they use the Hamming distance, and I don't really understand why you would need to do that unless they're just kind of showing you what it is. Here, I'm actually going to need my little notepad thingy again. So, oh, hold on a second. Let me pause it real quick. I got to figure out how to make this turn on. Okay, I got that working. So I'm gonna tell you how the way I learned how to do it, and it's going to use the method we previously used, kind of the same concepts, because they tell us how to do it here. They basically say, check each, like divide them up into blocks of 2, like if the key size was 2, and then you're going to compare them to each other. Well, they only have you doing it to the next one. And then you do that for every size, and the one that has the lowest Hamming value is the most likely key size. And then you take that key size, you think that's the key size, and then we can break the encryption the exact same. Like, so we know that say the key size is 5. Is that the example they use? I don't know, whatever. So if, let's say you know the key size was 5, then that means every 5th letter of the ciphertext was encrypted, was XORed with whatever the value of the first digit or first character in the key is. So we can create a ciphertext that's nothing but every 5th letter, and then we can find the single byte XOR key exactly the same way we've been doing. Like, we're just going to reuse, what was that, challenge 3? We're going to reuse challenge 3 again, and we can find it. So basically what we need is the length of the key. Now, the way I learned how to do it, and I don't know why they're using the Hamming distance. Like, it'll work, and so I'll actually go ahead and code it using the Hamming distance so that, you can at least see how you do the Hamming distance, and it'll work, and I'll explain why it would still work for the Hamming distance. But I think the way I learned is, that's how everyone is. The way I learned was the better way. Basically, let's say our ciphertext was just a bunch of, I don't know, I'll just put some letters: A, G, Z, X, Y, B, B, D, A, R, P, Q, F. Okay, that's good enough. And then it just goes on. What we can do copy it. Okay. So if we basically made a copy of it and sat it one on top of each other and shifted it over by 2 spots, right? And then we went through each one, and here, I'll do it with my cursor, counted up where the characters matched. Like, there's none here, but let's pretend there was some. And then so we said, okay, when we shift it by 2, it turns out to be that there is 7 characters that match over top of each other. And then we shift it by 3, and we go through and count them all, and shift it by 4. And they're telling us to do it everything for 2 up to 40. So the one that is the most likely key size is, 3, 4, 5. I'll use this for example. The one that is the most likely key size is the one that ends up having the most matches. So let's say if we shifted it 5, and it ended up being like, let's say for 2 there was, 7 matches, and 3 there was 9, and 4 there was 6, and then 5 would be something like 19. Like, it'll be a much higher number. And you're kind of like, whoa, that doesn't make any sense. Why does this work? Like, is it magic? And if we go back to thinking about what we were doing in, was it challenge 3, where we did the with the vectors. So remember, the key concept I wanted you to take away was that the value when you take the dot product of the two vectors is going to be highest when the vectors are identical, because the biggest numbers match up with the biggest and the smallest match up with the smallest. Otherwise you end up where, if it's just random, the biggest in general gets, matched up with one that's, much, smaller. So if we look at it, if the key size actually was, we're going to say it is 1, 2, 3, 4, it's 5, right? So then these characters here, the whatever, since say in the English language, what were our values? We'll use 3, or E as an example. So 10% of the letters are going to be E, and let's just pick another one. Well, it's A. Oh, okay, 6% are A. So if we go back to here, we know that these letters here were encrypted or XORed by the same key, right? Because if we got the key size right, this is the first letter. Actually, for 5, I'd want it shifted over more, because we're shifted 1, 2, 3. Yeah, this would be a key size of 4, but whatever. Oh, fine, let's say it's 4. Let's say we're lined up right. Just work with me here. Each value on these was going to be XORed by the same one. So for some random character or some random position, let's say, the 50th position in this list, the odds that it originally was an E are going to be the same as the odds, the one below it was originally an E. So like when you end up writing out the vectors, now it won't, what it'll be is like, I can't explain this very well, I don't think. But like when they're both B's, it means they were both the same character, under the original one. So if when it lines up, it has the highest chance. So like let's say I'm trying to think of a concrete example. So let's say we had our vectors again, and this is let's say the top one actually ended up being, when they don't match, let's say the top one was encrypted under 2 and the bottom one was encrypted under 4, and we're trying to see if these positions match, and we'd get all the values right. Since they're not the same, they wouldn't line up. Like, let's say 3% of the time is that, and 0.05, and this one was 10, but the 0.10 over here is a different spot. Like they don't match up. So the odds that they're going to be the same is, if you take the dot product, would be like let's say the odds that this letter was originally an E is going to be whatever the value is in that ETH position. So I don't know, let's just say it was, well, actually, so in A, the odds that it was originally, I'm not doing this very well. The odds that this originally was an E would be whatever then would be in the, that would be in the A. The A would go to the E. But basically what I'm trying to say is, if you don't have the right key size, the vectors aren't gonna line up. But if they are the same key size, then these were all encrypted. Like if this was the same key size, these were all encrypted by the same key, these were all encrypted by the same key, these were all encrypted by all the way down the line there, because it's all lined up, right? You've got blocks of the key size, and so the odds that they're the same letter is the odds the odds that it's, so if it's the letter A, that'll happen 6% of the time, times the odds that this was the letter A, and that'll happen 6% of the time. The odds that this letter could be a B, you add them together, so it's whatever the odds of it being a B are. Yeah, maybe this is a better way to explain it. So the odds you get the same letter is whatever the odds are that this is an A times the odds that this one is an A plus the odds that it's a B. Like if we didn't even consider this and I said, oh man, I'm doing that again. If we couldn't even, like that's so bad. Whatever. So let's say we can't even see this list. Like we don't know. We've shifted it over, but like, so the odds that the 50th letter in the top list is the same as the 55th letter in the bottom list, both under the same, because if the key was 5, it's going to be the odds that the top letter is an A times the odds that the bottom letter is a B plus the odds that the top letter is this, or the odds of the top letter is an A times the odds the bottom letter is an A plus the odds the top letter is a B times the odds of the bottom letter is a B. And if we end up doing that out, it looks exactly like the dot product because we're taking, this would be the odds of the C times the odds it was a C. So we're taking the dot product. And as we've seen, the dot products can be the highest when they're exactly the same. And when they're going to be exactly the same is the place where all the letters are encrypted by the same value. And that's going to happen when you get the exact number that the key was shifted by, or a multiple of that. Like say the key size was 5. If you shift the top one over 10, they're still all going to line up. So really, you don't need to take the Hamming distance. You can just count the number of duplications. Like you just shift the top string and then look and be like, oh, okay, there's 40 matches when we get to key size 7. So and that's way more than any other one. So it's probably 7. The reason it'll still work for the Hamming distance, like Hamming distance is like, let's say we have some byte 1011 0111 and then another byte 0111100, and you want to get the Hamming distance between them. It's basically the count of the number of places that the bits differ. So, which, as we know, is exactly the same as taking the XOR, but we'll just count. So there's a 1 there, a 1 there. These are the same. Those are different. Those are different. Those are different. So like 1, 2, 3, 4, 5, 6. These differ in 6 places. So the Hamming value of those two, or the Hamming distance, would equal 6. And we'll see if we XORed them, we'll get a 1 everywhere they were different. I should have wrote this bigger. 0, 1, 1, 0, 1, 1. And then if we count the number of 1s in the result of the XOR, we'll see there's 6. So basically, to get the Hamming, you can XOR them together and then count how many 1s are in the result. And the reason this will work exactly the same as if we just counted occurrences is because when 2 bytes are the same, and you XOR them together, right? They're the same in every position. So anything, as we said, anything XORed with itself is 0. So that's why if you do the Hamming distance, it'll still end up working out because you get a much lower number when you have a whole bunch of occurrences that match, and all the other places should essentially be random, so that'll even out. But I don't know. To me, it just seems better to take. You could count the number of occurrences. It'd just be simpler. And then also, if you're ever doing this by like hand, like if you have a cryptography class and the teacher makes you learn how to do this by hand, it's a lot easier just to count occurrences than take the Hamming distance. But I'll go ahead and code it up with the Hamming distance just because they're asking you to, and then you can see how you would do it. with a Hamming distance. So this should be, I'm pretty sure the next two challenges are pretty simple, so this should be the last. So we're going to need our XOR function, because that's how we're going to calculate the Hamming distance. So we can get that. We know our input is in base 64. So we're going to go ahead and import base 64 decode. And then I know from challenge 3, we're going to want our get single byte XOR, because that's how we're going to break it once we find the key. Get single byte XOR. Yeah, that just returns the key bytes. Cannot type. And then we'll have our if and our main. And we are going to parse our input. Now the reason I never write like a general purpose parse input for these is just because like each time the input's different, and so it'd kind of be a pain in the ass. And these functions are never very big to write anyway. So challenge 6 text. And then once we have our parsed input, we could go ahead and say the key size is get key size, and we pass in the ciphertext. And then once we have the key size, we could say, we could just get the key. Yeah, so key size. Yeah, then we could say key. Do we want to do it that way? Because yeah, we could say key equals. Yeah, let's do it this way. Get key, and we would pass in a ciphertext and the key size. And then we could say, what do they actually want us to do? Just decrypt it? That makes sense. Once you got the key, you can decrypt it. So let's go ahead and say our plain text is equal to the XOR of our ciphertext and our key. And then we'll go ahead and print all this gibberish out. Let's know what the key is, just because that'll be interesting. And then let's go ahead and just do a new line. Oops. And then our plain text will be that. So we'll write our parse input first. And it is, so this should all just be one line. I think they just did it this way for formatting. So with open name data, oops, data is going to be f.read. We want to, we could just replace every new line with nothing. And then let's go ahead and just return bytes, since we end up being wanted to work in bytes. So if we just base 64, I think this needs to be in bytes. So data, so f read replace in. First off, it's not base 64 or 5. Yeah, let's go ahead. Oh, we need to, yeah, so data equals, how do I convert a string to bytes? Actually, weird that I don't know how to do that. I usually can just type B in front of it, but I can't do that here. String argument without, and well, let's look it up. Convert string to byte string. B. Yes, okay, I'll eat your cookies, go away. Byte array source encoding and errors. String. Oh, yeah, I don't know why I'm having trouble with this right now. Duh. It's just I could just do it this way. So let's I need a break. Return base 64 decode data. All you have to do is just add encode to it. I don't know why I struggled with that. So now we're returning bytes. All right, so now we just need to write get key size, and we're going to take bytes, and we're going to return an int. That's what our key will be, a length. And then I'm going to go ahead and just put the header for key, and we're going to take bytes and an int, and will be, oh, why does that not look right? An int, and we're going to return bytes. And oh yeah, we only need these two functions right now. Okay, so when we get the key size, we basically want to get the Hamming count where each, we'll go ahead and shift it, so, or the Hamming distance. Well, okay, so we want to get all the possible Hamming distances. So let's say Hamming distances. I know we're going to need a Hamming distance function. Hamming distance, and it's going to take 2 byte strings A and B, and it's going to return an integer that is the distance between them. Okay, so Hamming distance is going to do, okay, we want to check everything from, what do we say, 2 to 40. I think we can do this with some list comprehension, make it a little more simpler. So let's go ahead and just do for I and range. It said 40, so we go to 41 because it never counts the last one. We want to get, we're having distances. We want to get the Hamming distance. Oh, I think I got to do this. The Hamming distance of oh, I don't know why I keep thinking we have a list of keys, but it's just a single key. Or I'm sorry, I'm thinking we have a list of ciphertext because of the last challenge, but it's just all one text, so we can just do it this way. We don't. Okay, so the Hamming distance of ciphertext. Okay, we'll do top. We'll think top and bottom. So we want the top one is going to be shifted over. It's going to be shifted over some amount, and the bottom one is going to start in the same place, but it ends. Oh yeah, we don't have to do anything with the bottom one. So if we just shift the top one and wrap it back around, so the first. Let me think how this would work. Oh, okay, yeah. So the first part of the thing is going to be what we shifted off the end. So we need to put that in the front. And it starts at -I and goes to the end of the list. And then we'll add to it what you get when it'll be the list, but it goes to it just goes to -I, right? So like if we shift it by 2, we want the last 2 bits of the text in the front, and then we want everything up to the last 2 bit or last 2 characters. So that would be one string, and then we're going to set that down on top of the other one, which is just the string itself. I for I in range. And that should be our Hamming distances. And then we want the one with the lowest Hamming distance. So we would say return Hamming distances index the minimum of the Hamming distances. Yeah, and that should be the key. So, and then our get key function we want to make blocks that are all built from the X letter of the ciphertext. So like if the key is 5 bytes or 5 long, we want the 0th index, the 5th index, the 10th index, yada yada yada. So I'll probably do this easier with list comprehension, but I'm gonna just do it this way because I think it'll be easier to write out right real quick. For I in range size okay, somewhere my thing isn't lining up. I'll worry about that later. We're going to create a block that is every ith letter. So we could say, oh, okay, we just say here I to the end of the string, and we go every ith letter, or every size of the key. So that will give us, so when it's 0 bytes, it'll go, does that work? What happens if you have, all right, I'll test it real quick. If we have a string that is A, B, C, D, F, G, H, I, J, 10 characters. long, and I say test 0 to -0. What happens? Yeah. What if I just, oh, I said -1, not -I, and then I go every 0th. Yeah, step cannot be 0. Oh, actually, I guess we don't have to worry about it in this case. Oh yeah, I don't know what I'm doing because we're stepping by size, not by I. I'm getting all mixed up now. I've been doing this too long today. I don't usually, what are we, a couple hours in now? I don't usually focus this long. I was thinking we're going by I, but so we'll be going from 0 to the end of the string, stepping by the size of the key. Then we'll be going from 1 to the end of the string. Yeah, so that's, and then by the time we get to, yeah, okay. So that should work. That should work. And then we'll get the key will be equal to, oh, actually, we just straight up imported it, so I could say get single byte XOR of the block, and then we can return the key. And then the Hamming distance, like I said, we want to XOR the two things together and count the number of 1 bits. So let's say the distance is 0. Oops, distance equals 0. And then we could actually just use, we do the whole thing with list comprehension, I think. Yeah, let's do it this way. It'll be easier. It'll be short. Well, I'll write it out the long way first, just so you can see how it's done in case it's not making sense. But like, so for byte 1, byte 2, and we're going to zip together A, B, which we've already gone over, kind of lines them up. And then, oops, there is 8 bits in a byte. So we could say we're going to do this loop 8 times. And then we can, actually, I'll do it the really long way. If B1 and 1 does not equal B2 and 2, oh, and 1, sorry. Distance is 1, and then we shift. All right, I'll go over this and then we'll make it look better because. So what we're doing here is we're going to line up the bytes and then compare the bytes. And there's 8 bits in a byte, so we're going to step through each position. Let me move that over. I can use this too. Don't lock up on me. Oh, I'd be pissed. So we're going to compare them. And the way you would do that is when you have whatever byte 1 is, let's say byte 1 was and you AND it with 1, an AND means take, if they're the same, it's a 1. If they're not the same, it's a 0. So 1 and 1 is 1. So that's how you get that first bit from any number, is to just AND it with 1. And then after we compare those, so if they weren't the same in the other one, so like let's say this was B1 and B2 equals 1, 1, 1, 1, 0, 1. And we ANDed that with 1 and it was a 1. And we're like, oh, okay, they're the same. So we don't do anything. If they weren't the same, then we'd add 1 to the distance. And then what this does here is we're going to shift the bit over to the right by 1 space. So like whenever you shift something, like so if we have 1001, and we were to shift that to the right by 1 bit, like this here falls off the end, and you end up with just 100, and you shift it to the right again, then you get 10, and you shift it 1, and then you just end up with 0. So we're shifting through all that, if that makes sense. A little bit operation for you. But we don't need to do all of this. We could shorten this up in the fact that we don't need to go, we could directly do the bytes, right? Because we've already said that we just want to count the number of 1 bits when we XOR B1 and B2 together. So we could just say B1 XOR B2, right? That's just going to be some integer. We want to convert that integer to binary, so we can. So like if we had a binary of 5, it's going to be 101, but it's going to print this OB thing in front of it. But what we can do, binary. What we can do then is use a string operator to count the number of 1s in it. And then, so we could just say, so like if we did that here, right, there's 2 1s in this string, so I should say 2. So we would just add that to the distance, and then we can return the distance. Or you can do the whole thing in one step with list comprehension. And you don't want to get carried away with list comprehension because you can end up making stuff harder to read, but I don't actually think this will be harder to read. So do it the way I normally do it so it makes sense. We know we're going to make a list comprehension, and what we're going to do is we're going to say for B1, B2 in zip AB, what do we want in each index? We want the count of the 1 digits of the binary when you XOR them together. And what is the Hamming distance? It's the sum of all those bits, or the sum of all those values. So we could just do it like that. So bam, there's our Hamming distance. Nice one little line, and I still think it's nice and easily to read. So I think, did we do everything? Okay, there's no chance this runs first shot, but let's see what we got. 6. Enter division or modulo by 0. So what we're passing into our XOR is not working right. So our key, oh, did I ever fix key? Yeah, key is bytes. Let's go ahead and print. Let's print the key and see what we get. It also could be the ciphertext. I parse the input. Let's print the key and see what happens. Okay, our key, we're getting nothing for the key. So let's make sure I got my ciphertext right. Okay, so we do have ciphertext. So key size equals get key size. Let's see if we're getting a key size. Probably we aren't. Print key size. Key size. Don't need that anymore. Okay, so this key size isn't working. So get key size. So maybe our Hamming distance. Maybe I screwed this up. What line range? binary 1, B1, B2, and zip AB. The count, we want to count the number of 1, so we want to return the sum of those. All right, let's see what our Hamming distances looks like. Oh, okay, that's why. Duh. So obviously the Hamming distance is going to be, okay, there's our key size. So you can, okay, so our Hamming distance is going to be the smallest when we don't shift at all. So what we need to do is, let's see, how could we fix this simply? I think we could just splice it. So they said to look from index or from key size 2 on. So if we just change that there, it'll ignore that and it'll get the minimum value from all these other Hamming sizes. And so you see like the Hamming here, you know, just for fun, I'm gonna go ahead real quick, like, because I think I can do this pretty fast. Let's do, I want to see show you how it works if you just do the coincidence counts. Take bytes, spit out an int, and then we're going to return the sum of 1 for whenever A, so A, B, in zip A, B, if A equals B. So that's going to be an array that's going to be either 1 or 0. It's a 1 every time they line up, or yeah, every time they match, and I'll return that. And then we can say right here, we could do coincidence counts, and then it's basically the same thing as above, except instead of Hamming distance, we're going to get the coincidence count. And then let's print out the coincidence counts just because I want to show you. And then we don't need that anymore. And just to do this, I'll make it quit right here. So you see when you don't shift the strings, they're obviously all the same. So 2,876 are the same. And oh, okay. I was like, what? One should be way bigger. Yeah, so you see 219, and the next biggest is like 59. Oh, there's a 67. But I mean, it's like significantly larger. And I guess Hamming distance is the same, right? It's I think this is much larger than this is, smaller comparatively. But like either way, you can see they both work. But I'll just keep it Hamming distance because why not? And then now I think hopefully this should work. Yeah, there we go. So our key size was 29. Our key was Terminator X, bring the noise. I think that's a song, and so then this must be the song. So let's print it out so I read it a little better. Yeah. All right, so I did do a little bit of debugging there. And it's just the logic flaw of not remembering that we don't want to check the whole list, because obviously the 0th index is going to be the lowest Hamming distance, because we're not shifting the top at all. So, all right, now we should pretty much, I remember looking at the next two and they're really easy. So hopefully you didn't watch all this in one go. And as all things, really, you should probably watch any video, especially something like this, in like 2x speed, because once you get good at it, like, it's not that hard to understand, and you just save so much time. Especially probably because I talk slow and I rambled on and screwed up all kinds of stuff. So what do we got here? Okay, yeah, so this is going to be really easy. We just have to implement AES, ECP via software. So let's get this. Resources, challenge 7 text. Whoops. No, don't do that. All right. So we have a key, yellow submarine, and we just want to decrypt it using. So, I mean, we're not going to implement AES like programmatically, so they want us to use, I mean, it doesn't make any sense other than to use like some module that actually has AES. So for this, I'm going to use the Pi Cryptodome package, which if you don't have it, you definitely want to get it, because it's like the one you're going to use. It's the one you use mostly with cryptography. You should just be able to pip install. And there's a Pi Cryptodome and a Pi Cryptodome X, and it says, I forget now what it is, but like, I don't know. I think the way I read it was like you should use Pi Cryptodome X. It has no conflicts if you have Pi Crypto. And I think a lot of distros still install Pi Crypto, but you don't really want Pi Crypto. I'll let you go down this rabbit hole yourself. But basically, I think the best way to do it is actually you uninstall Pi Crypto, and then you just install Pi Cryptodome. And I don't know why, but I think your Pi Cryptodome X is the one. But everyone I see just uses Pi Cryptodome. Anyway, just, I don't know, I'll let you homework, figure that out yourself. But basically, you want Pi Cryptodome. It's the cryptography package that you're going to use mostly if you're doing like cryptography stuff in Python. Well, this kind of stuff. So we're going to import the AES module, and then we're going to, I can't remember if padding is capitalized or not. I think it's capitalized. We want to unpad because we're going to be decrypting something, so it's going to have been padded, and we're going to want to unpad it. Our file they give us is in base 64. Port B64 decode, and then we're going to if all right, and then so they told us the key is yellow submarine, and the ciphertext is, we're going to parse our input, and it is in resources, and then we are going to create our AES. We give it a key, and we tell it what mode we're using. This way If not, the Pi, I'm just going to do it. Pi Cryptodome docs are pretty decent. So like Pi Cryptodome, AES, ECB mode. ECB. I mean, it shows you, well, this is for CBC. Well, anyway, their docs are pretty good, so. And then our plain text is going to be what happens when we decrypt the ciphertext. And since it's going to be padded, because it gets run through padding before being encrypted, we want to unpad it. And we need to know the size of the padding. And that is just going to be the block size of AES. So padding, if you don't know what padding is basically, you can't, your text has to be, your text you input into AES has to be the size of a block. So if you have something, so like they told us yellow submarine was exactly 16. So if you had something, so that's the size of a block. If you had something that was 3 bytes short of a block, padding schemes are different, but kind of, I think this is PKCS7. I don't think they say, but is basically where you pad it with the number, you pad it with the byte of the number of bytes of padding. So like we're 3 bytes short of being a full block, so we would pad it with the byte 3 times. So, and if we were 4 bytes short, like if the R was gone, it would be X04, 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 and etc. So that's basically how that version of padding works. Actually, you know what? I won't unpad it, so I can print it out and show you what padding looks like. And so we will print PT, and so it'll still be in bytes, so it'll print it out. So all we need to do now is just parse our input. So with open, let's see, the file is, okay, so it had all those new lines. We don't want the new lines, so we're just going to remove, replace. I think it was replace. Oop. Yeah, because we're not removing. We're replacing it with that, and then we will return the decoded data. And I'm going to bet this one works on the first try. I don't think I typoed anything. Incorrect AE. Oh, so I spelled yellow submarine wrong. Yellow submarine. Damn it. Okay, yeah, so see, blah, 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 blah. And at the very end, we were short by 4 bytes. So it's X04, X04, X04. So if we want to unpad it, this will remove those 4 bytes, and it knows to remove 4 because it just looks at the last byte and sees X04 and knows, okay, there's 4 bytes of padding. And all of this is going to play a big role later on. Padding will, because block size. Padding, you can break a lot of. ECB mode has no length. Line 84 in unpad. I must have given it something wrong. AES mode ECB. Are my parentheses in the right spot? Oh. I don't want to unpad the cipher. That's what I get for not really looking. I want to unpad the plain text. ES.block size. Now it'll be all that with nothing on the end, and then we can just decode it so it looks a little prettier. But yeah, padding, you can break a lot of crypto with like insecure padding, and if you have like what's called a padding oracle, I'm sure there's going to be a bunch of that stuff. So don't worry, if you want to learn all about padding, you will get the chance. So now we want, okay, so, I should use my thing again. Actually, I'll just use, so what we're going to do here, let's go ahead. Let's go ahead and get, yeesh, there's a lot of them. What if it all fit in the clipboard? Text. Oh, looks like it did. Well, maybe. So in this file are a bunch of hexacoded ciphertext. One has been encrypted with ECB detected. Okay, yeah. So ECB, I can show you the picture. ES. Yeah, here we go. Here's ECB mode. So, come on, blow it up. Okay, yeah. Make it bigger in case so you can read it. Okay. So when you have ECB, the plain text just gets encrypted and the ciphertext comes right out. There's no kind of like anything going on here. So every single time you give it the same plain text, if it's the same key, you'll always get the same ciphertext. So like I think they show the famous, so this is kind of a famous example of how ECB can leak information, because like, so they encrypted this image with ECB, but since the plain text always equals the same ciphertext, all these colors are the same, so every single block of white got encrypted to the same value. So you can see kind of bleeds to the image, where this would be what it would look like it should be randomly. So that's kind of how don't use ECB. And you can see here, this is CBC. What happens is there's an IV and that's chosen randomly. So the plain text first gets XORed with that, and then the resulting ciphertext is XORed with the next block of plain text. That way, if you start out, so if you were to encrypt something here, it's going to be, and you encrypted the same thing here, it's going to be different because there's these stuff's getting mixed in with it, so to speak. So anyway, that's how ECB works. So to detect ECB, so we've got these, how long is one of these? So let's say this is our ciphertext. How long is that? So 320 hex characters, so it's 160 bytes, because 2 bytes or 2 hex characters, takes 2 hex characters to make a byte. And an AES block is 16 bytes, so we've got 10 blocks. So each message is 10 blocks. Basically, the way we're going to find out which one of these was encrypted with ECB is we're going to look and see which one has some duplicates, because then that meant that I mean, you could have ECB and not have any duplicates, so this like wouldn't guarantee you to be like, if you can't control the input, like if this was just some random message encoded in ECB and all the other ones was random, like we wouldn't really be able to tell. But since I don't know, it's a challenge they're giving us, clearly it's going to be where we can. And if you can control the input, like if we had an encryption oracle where we could give it whatever input we wanted, we could tell whether or not it was encrypting with ECB because we could just give it one big long ass string of capital A's, and when we get the resulting ciphertext, there's going to be a whole bunch of blocks that are the same. So yeah, basically all we're going to do for this challenge is oops, sorry, I turned that off. We're going to see which one of these has duplicated blocks. So main. So let's say our ciphertext equals parse the input. Oops. Resources. Challenge 8. And then we're going to let's do a truthful. So we can just let's do so our ECB block or any ECB blocks. Did they say there's only one? Yeah, one of them. But let's pretend they're something. We're just going to do another list comprehension. So for CT and CTs, if contains dupe blocks CT, then let's input that there. And we're only going to get one back, but then we could print, yeah, we'll just print this out. It should be a list containing one block. So, whoops. Let's write our parse input function first. The easiest. Whoops. So we want to read it all. We want to split it on new lines. And then we can just return that. Yeah, because we don't need to do any kind of decryption or anything else. So we can just keep it as a string. It'll be a list full of each ciphertext. And then, so now we can do our contains do block function. We will give it a list of ciphertexts, and it's going to output a Boolean on whether or not it contains lists. So we're not going to do any error. Like, we're just going to assume that it's we're giving it one that's the right size. So we'll make a list of, oh, you know what we could do? Okay, yeah, this will be easy. So our blocks, we're going to make a list. So we're going to give it a ciphertext, and then we're going to cut that ciphertext up into blocks, and we're going to put it in a list. So do it the way I did before, where it's like, I don't know, my brain stopped working, so I'll just do it this way because I know it'll work, even though it might be uglier. So we're going to go from 0 to the length of the ciphertext, and we're going to go by 32. Like an AES block is 16 bytes, but in hex, that's 32 characters. And we're going to say in each block we want it to be I, whatever I is to and 32 positions later. And then here's the part I was so excited about. So the way we can quickly tell there's duplicates without like having to check each one or whatever is if we convert a list to a set. So a set is a mathematical structure where there can't be duplicate elements. So if we just convert the blocks to a set, or yeah, we convert that list to a set and we get the length of that set. If it's not the same as the length of the blocks, then we know there's at least one duplicate block. So yeah, so the length of our blocks is not the same as the length of a set of blocks. We'll return that comparison value. Yeah. All right, what do you think? Gonna work on the first try? You've probably spotted some typo and you've been screaming at me the whole time. You did that wrong. Damn, I didn't return something. Oh, ha! Is that what you were screaming? You didn't return data. CT is not defined. Oh, I don't know why I called it CTs. Oh, and it's not even a list. Right? Yeah, because I'm taking, yeah. Yeesh. It's sloppy. So, well, as you can see, that error, and like here, watch, I'll leave it as, what did I say it was, a list? It's still going to work. Yeah, so here's our duplicated block. So yeah, but really what it is I passed it a single ciphertext, which is in bytes. If I was using IDE, or I think it's called a linter or something, I would have gotten an error and stuff, but if you're just doing it in Sublime Text. Anyway, so what is this? Probably like over 2.5 hours long. So I can't fathom somebody made it to the end of this, but if you did, I don't know. I'd love to hear from you. Just leave a comment. Maybe I'll give you a prize. I'm just saying that because I don't think anyone will ever actually make it. But anyway, so hopefully if you did watch this and you did make it, or even if you watched some of it, and I'm not talking to you because you quit, you only watched some of it, but I hope you got something out of this, and hopefully I'll just suck it up and just upload it, and maybe I won't even watch it, because I know I'm just going to see all kinds of like errors and cringe and all kinds of stuff. But yeah, hopefully, yeah, here's hoping someday we all look back at this and go like, oh man, he used to suck so much, but now he's way better. Yeah, anyway, thanks. Have a good day.